Well, good afternoon, everyone. My name is Karina Apodaca from CSU Sierra and the Hurricane Research Division at NOAA Atlantic Oceanographic and Marine Laboratory in Miami. And the title of my talk, or what I will speak about today, is an initial assessment of a new data assimilation capability for GOES-16 and 17 satellites in NOAA NCEP systems. And I would like to acknowledge my co-authors, the other Supansky, and I don't mean the satellite, so Milia, with whom we co-developed the theory for the assimilation of this new observation type. And also, well, Lydia Kukrul, my supervisor at NOAA HRD, and John Derber, who's now retired, as you may know, was the person who encouraged the implementation of this observation operator in the NCEP system. So we'd like to acknowledge them. And improving the predictability of high-impact weather is one of NOAA's grand challenges. And for that reason, we have a lot of data flowing from new observing system missions, which has the potential to improve environmental analysis and prediction in operations. However, the impact of new observation type in operations has to be thoroughly assessed before the inclusion of a new data in operations, and especially in the data stream at NOAA NCEP. So the NOAA Observing Systems Council, under the Quantitative Observing System Assessment Program, it has the responsibility of evaluate the impact of observations, mainly via observing system simulation experiments and observing system experiments for the new observation types, while the other for the future, in global and regional operational forecasting models for the atmospheres and oceans at NOAA. So this is the primary role of the COSAP program, which Lydia Kukrul is the deputy director of science director of COSAP. However, COSAP also supports the development of and evaluation of new observation operators that can improve initial conditions and predictability for operations. So the rest of the talk, I will focus on the lining observation operator, which was implemented in the Gridpoint Statistical Interpolation, which is used operationally at NOAA. Actually, COSAP has been tasked to evaluate the capability of this new observation type in the FV3 GFS system. But before we get to that point, well, first I will focus on the talk on what or how the observation operator was developed before we get to that point. So as of now, this new lining observation capability has been incorporated in the operationally used data simulation software at NOAA since last October. In last year, so fairly recently. And so what is the observation from the GLM instrument that gets assimilated? So the GLM instrument detects, it's an optical transient detector. It's a fancy term for I would say, a very expensive camera that has a satellite view or a view from space of changes in the optical scene, and that's how it detects lining. So it's only a two-dimensional field at the surface, what it can view from space. So the simulated observations are, in the end, a cumulative count of geolocated groups. There are flashes, groups, and events, and we have seen from other colleagues that actually the groups do have a better, the detection capacity for those, it's much better with the GLM instrument. So in typical data simulation time window, we count the number of strikes or groups, lining groups, per unit time, per unit area. So in the end, this is the assimilated observation type. So now for the development of the observation operator. So for this new capability, actually the algorithm itself is suitable for global and regional analysis and prediction in the GSI, or the version of the GSI is the Global Data Assimilation System for the global system itself. So it is based on the relationship between lining vertical velocity and either a sum of cloud hydrometeor content, ice and water, or the total, or speciated in the new FV3. So, I mean, for the new FV3 or regional prediction systems. So for the GSI, it has to follow a variational framework. So we have, in this case, a nonlinear observation operator. Then we have to linearize it, so to compute the tangent linear. And then we have to develop an adjoint model for it. So the algorithm starts with the calculation of, given that relationship, it starts with the calculation of vertical aft-draft speed via the nasty continuity equation. Then the algorithm branches out to global or regional cam scale data assimilation via some logical flags that are prescribed on a name list. For the global system, we use a simple formula. It's a regression formula based on the empirical relationship between lining flash rate and some sort of threshold of hydrometeor content with some parameters based on satellite climatologies. And over there, W max is the maximum aft-draft speed. So for global GSI analysis, the nonlinear lining of flash rate observation operator is a function of our usual GUIs, our usual control variables, pressure, surface pressure, temperature, specific humidity, and the horizontal wind components, U and V. But for the regional branch of the algorithm, so for or a cam scale, by the way, cam scale, convection allowing model resolution. So the lightning flash rate algorithm, it's a function of, it's a combination of two things. Vertical fluxes of grapple, and then a horizontal distribution of other species of hydrometeors. So grapple, the sum of grapple, snow, and ice. And all of this are in the mixed phase region, or for mixed phase clouds. And then again with some interpolation coefficients. This is suitable for lining formation or originated in continental type of convection. So the advantage of this branch of the algorithm, it's we can also have a relationship between the large scale dynamics, humidity, and then the small scale cloud microphysics fields, or cloud variables, as well as the environment. So actually, due to the use of the continuity equation for the calculation of vertical velocity, and in that equation, to compute the tangent linear, we need to use a finite difference approximation method. For that, we use a halo of 12 grid points surrounding an observation. So two things happen. We read our background fields at this location surrounding an observation. And then to compute the Jacobians, or the perturbed state, we also used this halo. So in the end, we compute the derivatives using this 12 grid points. So for the tangent linear, we need to, of course, minimize a cost function, three-dimensional for the variational solver of the GSI system. So we need to take, of course, the gradient with respect to all of our inputs, our control variables. So this is the example for the top equation. Oh, there's a pointer here. So for the global branch of the algorithm, so with respect to temperature, humidity, and the U and V components of the wind, and a similar procedure is done for the cam scale branch. Of course, it would include a much more complex equation from what I showed earlier for the tangent linear. And this one has the capability of updating 7 control variables. So the first variation, the Jacobian yields the elements of the observational Jacobian matrix for all of my control variables. So in the global branch, we can update 4 and then 3 more in the regional branch. So then follows the calculation of the adjoint model. Simply follows, of course, from the tangent linear. And then in the end, for the global analysis, the adjoint produces the gradients of specific humidity, temperature, and the horizontal wind components. But for the cam scale, in addition to the gradients above, we have gradients of ice, snow, and gravel. So lightning flash rate observations can impact the analysis increments of environmental variables that support the storm formation, basically, but also like the finer scale cloud variables. So some additional features of this capability, it includes a cloud mask. This way, we can perform the calculation of vertical velocity. This is the main driver of the relationship between, basically updraft speed, separation of hydrometeors, and then aligning spark, if you will. So this ensures that we only do the calculations where clouds are present. For the global system, we use a threshold of total hydrometeor content, but for the regional, we use the location of a mixed phase layer. So in the end, for the observation operator, we end up with a 2D field, a two-dimensional field at ij points of lightning flash rate basically at the surface. It also includes a variational bias correction type for innovation statistics and based on optimal parameter estimation. Oh, that bell. So some verification. I'm almost at the end of my talk, luckily. So we can see, so left some raw surface observations, and then which were initially used for testing prior to having access to GLM. And then this is actually what is processed by the GSI system, and we can see that the location is pretty decent. So for the global system, we can see already some impacts in the analysis, and they happen at the location of the lightning observations and where weather is happening. Probably, I'm not sure if I included that slide, but yeah, the locations are coincident. But for the cam scale branch of the observation operator, we can, but this is just a single observation test at the location of a lightning strike. And then we see what we expect. So lows of positive and negative analysis increments at either side of the observation for temperature and water vapor mixing ratio in this case. And then we see some circulation around the location of the single ops. So, so this allows for an explicit quantification of control variable updates. And since we have hydrometeors as control variables, we can see already some differences between a control and and an experiment where lining was assimilated. So in preparation for now FB3 GFS, we had to make several changes to the algorithm, hopefully not that many. But actually in non-hydrostatic, now GFS FB3 is actually a non-hydrostatic model. So W is prognostic. So you can avoid the calculation of W, but at the expense of having less control variables being updated. So it will be W and then the other guys. But by doing an extension to the ensemble-Kalman filter in the hybrid for the M-bar, might impact other fields through cross-covariances correlations. But whether this will happen, I'm not sure. And then, so now FB3 uses GFDL microphysics. However, for now, they're prognostic. The hydrometeors are prognostic, but they're not fit back to the model yet. And then some folks at NCEP, EMC specifically, they're testing more complex microphysics schemes. In the end, they will tell us which one they choose. However, this will not affect us as long as the hydrometeors that we need are present. So if in the end this hydrometeor feeding to the global system occurs, we can adapt the regional lining operator actually to the global system. For now, the regional is a viable candidate for lining DA at CAM scale efforts, like similar to the rapid refresh NOAA SRO. And to summarize, well, the first version of the GLM assimilation in the operational is now in GDAS. I must say that also the community version of GSI has this capability. It was released sometime in the fall-winter of last year. So it's available, and it's hopefully well documented in the program. So, so the variational assimilation framework for this capability can update 4 to 7 control variables. So what's coming next, and this is the work at COSAP. So we will do OSE type experiments, in cycling experiments with FB3 GFS. We will use the coarse-resolution initially, because that's our computational capability at the moment with a 20-member ensemble. And future, I guess, for final testing evaluation, we will increase the resolution both for the deterministic and the ENKF. So we will determine also the optimal configuration of all the operational suite of observations with lining. And initial testing of this was planned for the next implementation of FB3 GFS, which is planned for this month. And with that, well, thank you very much for your attention. That's all I have, and I will take questions. So thank you for the organizing committee and scientific and the local folks. And this work is being done on the auspices of the COSAP program. And please tell me that that says things, because I'm not sure. So hopefully. So thank you very much.
Thank you, Karina.